Hi, welcome back. The 3n+1 conjecture says all numbers go to 1, and there's no other loop out there where numbers go round and round without reaching 1. So we're trying to prove that no such loop exists. We can't do that yet, but there's progress. For example, all numbers less than a billion billion go to 1. So any loop can't involve small numbers. Also, there's no loop with fewer than 10 million members. And we know that there's no circuit loops that go up and up and up, and then down and down and down. So in this episode, we're going to rule out a bunch of other types of loops. So let's start with a reminder of why there's no circuit loops. This 3n+1 computer lets us calculate the value of the bottom member of a circuit loop. We push all the up moves to the left, then we multiply these increasing powers of 2 with the decreasing powers of 3, and we add up all those products, getting beta, which for a circuit loop amazingly simplifies to 3 to the x minus 2 to the x, which we divide by 2 to the k minus 3 to the x, and that gives us m, which if you put m through the circuit, we get m back out. If you want to know why this 3n+1 computer works, episode 11. Okay, so we just need to show that m is never an integer. So here's m for the loop length k equals 65 with x equals 41 up moves. Is that an integer? I don't know, it's hard to tell so far. So what we're going to do is assume it is an integer and see if we can reach a contradiction. If this is an integer, then so is this. It's like if you knew 42 over 7 was an integer, then you could conclude 42 plus 7 over 7 is also an integer. And our numerator just got bigger, but that's okay because we can take out these 3 to the x's. Anyway, this also has to be an integer. And since x is less than k, we can factor our 2 to the x out like this, and this also has to be an integer. And here's the key step for the whole thing. We know that the denominator is odd with no factor of 2 of its own, so we can cross off this 2 to the x in the numerator, and the whole thing still has to be an integer by our original assumption. So, but we just knocked off a factor of 2 to the 41, so this result is really small, and it's not an integer. So our assumption must have been wrong in the beginning, which is what we wanted to show. Now, this is small in this case, but can we show that the denominator is always bigger than the numerator, like this, with 2 to the k minus 3 to the x. Here we're asking about the distance between powers of 2 and powers of 3 down the number line. And Baker and others have shown that this distance grows really fast, certainly faster than 2.5 to the x, which is bigger than 1.5 to the x, which is bigger than the numerator, which we can show in a couple of lines very easily. Basically, if we assume this is an integer over here, then we need more up moves than down moves. Okay, so stepping back, this proof has two components. One is arranging to factor out 2 to the x and cancel it. That's a typical factoring technique involving only integers. The other is showing that the new numerator is smaller than the denominator, and that's more of a magnitude technique involving real numbers. So we can combine these factoring and magnitude techniques to rule out other kinds of loops now. So here we've got a loop with 2 up moves, 1 down move, 2 up moves, 1 down move, etc. So there's an even number of up moves, so x is even. Just like with the circuit loop, we can show that this type of loop never consists of integers. This loop's beta simplifies to 5 times 3 to the x minus 2 to the 3 halves x. Hey, where's that 5 from? Well, if we look at any pair of pieces like this, we've got 2 to the a times 3 to the b plus 2 to the a plus 1 times 3 to the b minus 1. And that simplifies like this. Here the 2 plus 3 is basically our 5. So let's show that this beta divided by 2 to the k minus 3 to the x is never an integer. So first let's assume it is an integer. That means this also has to be an integer. Here we've added 5 denominators to the numerator this time. So this also has to be an integer, and this has to be an integer. And here's the key trick again. We can cross off all these 2 to the x's and wind up with something even smaller than we got last time. So with this green card, we can easily show the denominator is bigger than the numerator, so it's not an integer. our assumption must have been wrong, and so there's no loops of this type. And we can do the same thing for loops that go up, 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 down, and so on. Here x is 3 even instead of even. So in this case, beta hilariously simplifies to 19 over 11 times 3 to the x minus 2 to the 4/3 x. And we can use our same reasoning. So hey, we're supposed to be talking about integers here. What's this 4/3 x and dividing by 11? Looks bad. Well, x is of the form 3m, because it's 3 even, so that's okay. And it's not hard to show that 3 to the 3m minus 2 to the 4m is always divisible by 11. So don't worry, we're cool. How about a loop that goes up, down, up, down, and then repeats that? Same thing. Beta simplifies like this. And we can arrange it so we have lots of 2's to cancel. So this is good progress. Of course, there's plenty of loops out there that don't exhibit this kind of nice regular pattern, and we have to show that they also can't consist of integers. Okay, see you next time.